So we're writing the standard form of an equation with zeros at 2, 3, and 1 minus I. So the key thing here is because that complex zeros have conjugate pairs, if 1 minus I is a solution, that means 1 plus I must also be a zero of the function. So we write it in factored form, and then we're going to multiply. So since 1 minus I is a solution, we'll take x minus 1 plus I suppose is the one we use here. So that means we'll use x minus 1 minus I as our solution. So then our other zeros were at positive 2 and positive 3. So writing it as a factor, you'd have x minus 2 and x minus 3. So they're wanting us to multiply now using the FOIL method. So first terms, x times x is x squared. Outside terms, 1 minus I times x. Inside terms, minus 1 plus I times x. Excuse me. And then the last terms, we're going to have positive 1 plus I, 1 minus I. So the key thing here is when they multiplied inside here, remember I squared is negative 1. That's the main thing you have to remember as we do this. Now they're just multiplying, they're combining like terms, and they're simplifying. So notice we've got the negative 1s that will add together. Meanwhile, the i's will go away. So it's going to end up with x squared minus 2x, and then plus 2 times the x minus 2, x minus 3. Then they just multiplied these binomials. So you can use FOIL. There's a nice easy trick. You know the first terms are going to multiply to that. You know the last terms are going to multiply to get positive 6. All you really need to do is add these numbers, and it's going to tell you what the middle piece is here. So x squared minus 5x, and then plus 6. And then they distribute again. So they took the x squared times this piece here. They took the negative 2x times that piece, and then the 2 times that piece. Multiplied everything out, spending a lot of work. Combining the like terms, you end up with x to the 4th minus 7x cubed plus 18x squared minus 22x plus 12. Normally, they won't look quite that messy. They'll look something more like this. So we want to write the function with zeros at 4 and 5i. So if we write it in factored form, we put x minus 4 and x minus 5i. But remember, since 5i is a 0, that means negative 5i will also be a 0. So that means we have to add in x plus 5i. Now, when you've got ones like this, it's easiest to multiply these binomials first, because when you multiply these, the i's will go away. If you FOIL, you'll get x squared plus 5ix minus 5ix minus 25i squared. So if we notice, those are canceling each other out. The key thing here, 25 times I squared is the same thing as negative 1. So this actually FOILs out to become x squared plus 25. That's the key here. When you work with these imaginary numbers, I times I is I squared, and I squared you have to replace with negative 1. So since we were taking x squared minus negative 25, it becomes x squared plus 25. So now we will FOIL again. We'll get x cubed plus 25x minus 4x squared minus 100. Writing it in standard form by power, x cubed minus 4x squared plus 25x minus 100. So the key thing to remember, if you have an imaginary as a solution, got a positive, you will also have the negative. They have to come in pairs. Now, solving real-world problems, we can use graphing to help us locate or approximate any real zeros of a polynomial function. We've seen that before. If we're talking about real-world problems, we're not dealing with the imaginary parts because our imaginary numbers don't fit in with the real world. So we've got a model that is approximating oil consumption over a period of time. We're trying to see where's it the same. So all you really need to do, graph these two functions and see where they intersect. The calculator, as we've seen, has a nice intersect function. The function, in this case, they intersected about x equals 5, which represents the year 2006. This means the models show oil consumption in the Asia-Pacific equaling and then overtaking oil consumption in North America about 2006. So we're really just looking where these functions intersect. All right, this one's a bit of a complicated problem. An engineering class is designing model rockets for competition. The body of the rocket must be cylindrical with a cone-shaped top. So we're going to have two pieces, a cylinder and then a cone. The cylinder part must be 60 centimeters tall, and the height of the cone must be twice the radius. The volume of the payload region must be 558 pi centimeters cubed in order to hold the cargo. Use a graphing calculator to graph the rocket's payload volume as a function of the radius. And on the same screen, graph the constant function for the desired payload, and then find the intersection to find x. So a couple of key things here that they're not telling you is really your functions, your equations you need for the volumes. So again, we're going to have a cylinder, we're going to have a cone. The equation for the volume of a cylinder is pi r squared h, and volume of a cone is 1/3 pi r squared h. So if we're talking about the volume of the rocket as a whole, we're going to have to add those two pieces together. The key things they told us is that the cylinder must be 60 centimeters tall. So the height of the cylinder is 60, and the height of the cone has to be 2 times the radius. So 2 times r, I'm going to use x instead. So when we think about the volume as a whole, we have to take the volume of the cylinder. So that's pi r squared h, so height of the cylinder is 60, plus the volume of the cone. So that's 1/3 pi r squared, and then times the height of the cone, which we said was 2x. So combining like terms here, doing what we can, we'll get 60 pi x squared plus we get 2/3 pi x cubed when we multiply it out. So this is our volume function. So we're going to graph this and the 558 pi. Those are the two things we're going to graph. And then we want to see where do they intersect. So we've got 60. Where's my pi? Pi x squared plus, in my parentheses here, 2/3 pi x to the third. And then we're also going to graph 558 pi. Now, I know I forgot to line up 558 pi. That's pretty high up on my y's, so I'm going to go ahead and change my scale. We'll take it up to, let's say, 600 pi. So I know that's higher than 558 pi. And then just for normalcy's sake, divide that by 10. We'll do increments of 60 pi. That's not a huge deal since we're just looking where they intersect. Well, something went wrong. Let's see. 60 pi x squared plus, oh, I know why. I changed the x values, didn't I? All right, come back and I will totally fix my mistakes again with the calculator. We'll finish up this problem.